Okay, so I'm starting with Steiner symmetrization, which is what I think you all know. It is the process of creating a convex body. This one, S. What did I do?
There is some button that you pressed and that made it. So just press the same button again.
So you have a convex body K, and you create a new one called SBK. This is symmetrization, which consists in taking so you take a direction B, and you chop K into vertical segments. Vertical meaning parallel to the vector B, and then you translate all the segments until the midpoint is in the orthogonal subspace. So then you create a convex body which is symmetric with respect to the reflection, respect to the orthogonal. Now this is not the only way of creating a symmetric set with respect to V. You can also, for instance, reflect it and then take the Minkowski combination or any other combination. One of these combinations is called the fiber symmetrization, which was defined by Gardner, Bianchi, and Gronch in a paper about the many symmetrizations you can do in convex bodies. And this is with respect to a subspace of larger dimensions. So you take a subspace F, which is this vertical line. Imagine it is 2 or 3 dimensional, and you consider the orthogonal subspace. Then what you can do is you can define a vector space operation, an addition in all the affine subspaces which are parallel to F. So you have F1 and F2, then you can just sum the F coordinate. This gives you a vector space operation. And then one way of creating someone that is symmetric with respect to the reflection respect to F orthogonal is to take half the differences of F1, F2 of the fibers. So if you see here, all the points in this segment can be written as the points whose vertical coordinate is beta minus alpha over 2 or alpha minus beta over 2, where alpha and beta are the vertical coordinates in the segment inside K. Okay, so this is the fiber symmetrization, and one observation is that if you intersect K with the affine subspace parallel to F, then what you get here is a convex body which has the same dimension as F, and when you take these differences, you obtain the difference body. Okay, so in each of the fibers, you are replacing the fiber by half the difference body, and this does not preserve the volume. In dimension 1, the volume is preserved because of Fubinian, because it's the same segment. But in here, the volume in general increases because of the Minkowski inequality.
And so you get n minus k dimensional body?
No, you get an n dimensional body. So each fiber is say m dimensional. You replace each of the m dimensional fibers by a new m dimensional fibers, and you have n minus m dimensional. So the points parameterized in the fiber is n minus m dimensional. So it's the body in the same space, but symmetrized with respect to something different. Okay? Okay. You don't believe me. It is in the same space. Now I will apply this fiber symmetrization in space of matrices, and this makes sense because there are lots of interesting convex bodies in matrix spaces. So I consider matrix spaces of dimension of n rows and n columns, and here we have lots of useful norms. For instance, the Hilbert-Smith norm, which is the Euclidean one, the vector norm, the trace norm, and the Schatten classes. There are more, of course, and here in the matrix space we can, if you have a n times m matrix, you can multiply from the right and from the left with d times m dimensional matrices or n times l dimensional matrices. I did this again. Okay, so if you have a convex body, you can consider the left and right action of multiplication by matrices. So by A times K, I'm referring to A times the point, where the point is itself a matrix, right? So these two operations are just linear functions applied to the convex set, but particular linear functions. Okay, so if you identify the set of matrices with m copies of Rn, you can look at the columns of the matrix. So if you have a matrix, you have the columns, there are m vectors in Rn. You can see what this action does with the vectors, and the left action, the action from the left, is just the diagonal action of the function t applied to each of the vectors, right? You have many copies of Rn, you apply the same linear function to each of the vectors. Now the right action does something very different. You can multiply by a matrix and swap the columns swap the vectors v1 with v2. You can make linear combinations with scalar coefficients, and you can, for instance, take one vector and you can obtain several copies of the same vector, scaled by numbers. And using this last action from the right, one can define a particular subspace of the matrix space, which is the subspace of consisting of matrices who has columns that are all parallel to a fixed vector v. Okay, so you fix a vector v, and you consider all these AB matrices. You can construct this 2n-dimensional subspace of the matrix space, and this is very useful in combination with fiber symmetrization. Now the space is the space of matrices m and m, and instead of f, well, f was an arbitrary subspace. Now I will consider v to the m, which is exactly what I just said. The set of matrices whose columns are all parallel to this vector v, and it can be parameterized by matrix multiplication to the right by some row vector t. This vector t is what I just called AB, like before. Then if you consider the orthogonal space is the set of matrices, this one, this X, whose columns are all perpendicular to V. All right? So this is an m times n minus m dimensional subspace, the orthogonal one, and I will consider the fiber symmetrization with respect to this decomposition. So any convex set L in the matrix space will be intersected with this subspace, a phi subspace, and then I will take half the difference body, right? And this operation gets along very well with the matrix multiplication, and that's why it's interesting in matrix spaces. So the symmetrization I'm going to use this S bar of B. So notice now that L is the convex body L is in dimension m times n, right? And the vector with respect to which I'm symmetrizing this V is in just Rn. It's in a different space. Okay? And now, okay, by doing this, I obtain a symmetrization in the space of matrices, and this has very nice properties. Well, the first is not very nice, is that the volume of the symmetrization increases. Okay, it's larger. This is not very nice, but when you try to prove an inequality, if it goes in the right direction, you only care about the good direction. Okay. Then if m is 1, then the set of matrices of only one column is just Rn, and this symmetrization is the usual Steiner symmetrization. Then it preserves convexity and it preserves exclusions. And in matrices, you have a natural product structure, which is if you take two convex bodies, then you can consider the matrices and you put them together, right? You put the first columns of the matrix of one set and the second column of the matrix of the other set, and you get a product structure. And this fiber symmetrization gets along very well with the product. So, for instance, if you have several convex bodies in Rn, and you take the product of all the convex bodies, then the symmetrization of this product will be just the product of the Steiner symmetrizations. Because if m is equal to 1, this is just the usual Steiner symmetrization. Okay. Okay. Okay, these are the good properties. It gets along very well with matrix multiplication. So first, from the left, if you have an orthogonal matrix, it happens what you expect. Then, if you take a body and you rotate the body, okay. Here A is an orthogonal matrix of size n times n. So you take one rotation of Rn, and this product AK is just the action of the n times n matrix on the convex body, okay, the diagonal action. So if you rotate all the coordinates diagonally and you rotate the vector, then the fiber symmetrization is just the fiber symmetrization of the original body and then rotate. Okay, this is what you expect with orthogonal transformations. But with the right action, the action on the right, it's much better, because if you take any matrix, if you take K is a convex body and A is any matrix, you can change dimensions if you want. If K times a body of dimensions n times m, okay, then you have an inclusion with any matrix. And this means, if the rank of the matrix is appropriate, is D, so then you have an equality. So for instance, if A is an invertible transformation, then you have an equality. So the fiber symmetrization is invariant by all GLM, which is a large group. This is a very good property. Finally, you can consider, so if you consider the multiplication on the right, you have matrix A, and you consider multiplication on the right, then this is a function, let's call it A bar. Then if A has the good rank, which has to be M, then the symmetrization also commutes with preimages of multiplying to the right. Okay? And these two properties, the 6 and the 7 properties, they are not related to one another. They look the same, but they actually property 7 is more related to this one, 4. Okay. Okay, so these properties are very good, and so the bad news is that the volume is not preserved. But so to replace volume, there are some other quantities that are preserved. So, for instance, the mean width is preserved. More generally,
no, you have not gotten this.
What happened?
You have less or equal.
Mean width is less or equal than mean width. It's not preserved, but it's less or equal. Yes.
You said preserved.
I said preserved, but I meant that it doesn't increase. So increase is bad. So an inequality is sufficient. Yeah, so in general, if you put this integral p equal to 1, you get the mean width. The p norm of the support function is also preserved. It's also diminished. Here there's a typo, because v is n times m dimensions. It's an integral in m times m dimensions. Okay. If you project onto one of the coordinates, for instance, then the volume goes down. Okay, goes down. So in particular, if you consider the product of the projections onto all the coordinates, which is, for instance, the volume-like quantity that appears in the Loomis-Whitney inequality, then this is preserved. It's not preserved. It goes down. Okay, so I'd like to have more quantities that go down, but these are the ones I have for now. And now, of course, there are invariant sets. For the Steiner symmetrization, the invariant sets are just the balls, right? And now, what does it mean to be invariant by fiber symmetrization? Well, it means to be invariant by rotations, by diagonal rotations. Okay, so if you have a convex body, this guy is invariant by the symmetrization if and only if, when you apply a rotation on the right, then you get the same body. So, for instance, if the body is symmetric, What this means is that a symmetric convex body will be invariant if and only if the norm is left unitary invariant. Okay? Of course, one could, for instance, play with the transpose. If you transpose, symmetrize, and then transpose again, then you will have a right symmetrization, and you will have a doubly invariant set if and only if the matrix is unitary invariant.
I'm so sorry, so is it not just a ball?
Not just a ball, no. So for instance, the operator norm with backspaces where the second one is Euclidean, this one is invariant.
What? So what sort of convex body?
What?
Can you give an example in terms of convex? So is there a convex body that's not a ball that's invariant?
What?
Like the product of a ball and...
The product of balls is invariant.
So the product
Euclidean
of a
ball is
ball and
invariant.
another body.
All the norms I showed you before, the Hilbert-Schmidt, the Schatten classes, all that, they are unitary invariant, so they are invariant by the symmetrization. But there are many examples. You can take a convex body and symmetrize it several times until you get an invariant set. Okay, you can do this. And also, I don't know if the limit set is unique. So if you consider, there is an interesting point here to be made. If you consider these bodies that are unitarily invariant on both sides, they are uniquely determined by their singular values. So if you have a convex body and you look at the singular values, what happens with the symmetrization? What's the interaction between the singular values and the symmetrizations? I have no idea what happens there. But I would be very interested in proving something like this, something like it converges to the unique body having these singular values. So
you mean ellipsoid would be in there? Yeah.
it depends on what am I affine image of the ball. If you take a ball and you take an affine image, which is a diagonal action of some function on the right, so not diagonal, from the right, then it will be invariant. But if you take a diagonal action from the left, then it won't be invariant. So this is just a silly application of what you can do with fiber symmetrization, which is consider the operator norms, right? If you have convex bodies, if you have a convex body in Rn and Rm, then a matrix will represent a linear function from one to the other, right? Then you can consider the set of matrices and an operator norm less than 1, where operator norm means, for me, the operator as in a Banach space operator, right? So the unit ball of the Banach operator norm as Banach space operators, it is the set of matrices X sending any vector of K to L by multiplication, okay, by matrix multiplication. So what you can prove very easily is that the fiber symmetrization of the operator norm of K and L is inside the operator ball of V and SVL, where SVL is the Steiner symmetrization. Remember that K and L are Rn and Rm dimensional, M and N dimensional, and so you symmetrize the arriving space in the usual way, and you get this inclusion. And as a consequence, since the inequality of volume goes in the right direction, this guy has larger volume than BKL. So the volume of BKL will be smaller than this one with the Steiner symmetrization. And if you repeat the process with many directions, you get an inequality of volume with L star, which is the Euclidean ball of the same volume. All right? So, and also interestingly, you can apply this argument of the transpose. You can transpose, then symmetrize, and then transpose again. And this lets you symmetrize the first body. So in short, you can symmetrize, you can replace any of the bodies with a Euclidean ball of the same volume, and you will get that the operator norm ball is maximized, has a volume which is maximized in this situation. And the proof is two lines. So the first one is that you take a point in the first convex body. So any matrix in this ball, when you multiply x times e, will be inside L by definition, right? And you consider this symmetrization times e. So e is a vector, is a column vector, but it's also a matrix. And you can apply the property of commuting with right multiplication by matrices. Well, matrix is now the vector E. So you get this inclusion. And now if you take an operator ball, so you take a point in BKL, which is a matrix taking K inside L, and you multiply by E, because E is in K, then this vector will be in L. So the inner multiplication will be inside L, and the fiber symmetrization preserves inclusions. And that's it. That's it. It's very simple. And then the argument with the transpose is that the volume, well, the set VKL is the same as VL polar K polar transpose. Okay, if you transpose the matrices, you get this other guy. So you can transpose. The volume is preserved by transpositions. You apply the previous theorem, and then you transpose again, and you get VKL. When instead of K, you get the polar, then the ball of the same volume, and then the polar. And because of the Blaschke-Santa law inequality, this guy is inside this guy, and then you are done. So the proof is extremely simple. You can do more. Like instead of taking the volume, you can take the integral of any function which has good properties with respect to fiber symmetrization. These are called the Steiner concave functions. So one example is the determinant to a negative power between -1 and 0. This integral will be maximized if you replace K and L with the balls of the same volume. So I thought this. So at first my idea was to use this inequality to try to bound the volume ratio of convex bodies, because if you know that this integral is small, then maybe you can say the argument that if the integral is small, then you have one matrix for which the determinant is large inside the operator ball. Okay, and this means a matrix with large determinant taking K inside L. This is connected to the volume ratio. Okay, there's another application which is some difference body that was defined by Schneider in the 70s that extends the difference body in the usual sense. If you take a convex body K and you consider all the M tuples of vectors in Rn for which the intersection of all the translates is non-empty, then this is what we call the DMK, which is the difference body with a multiple variable, something like this. So in the case M is equal to 1, you only have one translation, and you get K intersection K plus X1. And this is the usual difference body, okay? Then what you can prove is that this body also interacts with fiber symmetrization, because you see this M tuple of vectors as a matrix, okay? And so as a consequence of this inclusion, you have that so Schneider conjectured that the volume of DMK was minimized when K is an ellipsoid. Because what happens is that in M equal to 1 case, because of the Brun-Minkowski inequality, the volume of dk is minimized by all the symmetric sets. Okay, but this is not the case in the higher dimensional setting. So using this inequality, what I can prove is that the mean width of DMK is minimized when K is a Euclidean ball. Okay? This is because the fiber symmetrization does not preserve volume, but it doesn't preserve the other quantity. So here you can put any other quantity that goes down under symmetrization. And the proof is again very simple. You can write the this DMK thing as a product of the convex body to the n+1 times a matrix to the right. And then you use again that the fiber symmetrization interacts very well with right multiplications. So you have just a chain of equalities until you get that the symmetrization of DMK is inside dm of the symmetrization of K. Okay. And then there is another application where I came to be interested by this, this symmetrization, which was a paper with I mean, my colleagues Dylan Langsat, Eli Putterman, Michael Royson, and Bianchi last year, and it's about this convex body. It's another way of defining from a n-dimensional convex body a higher dimensional convex body which resembles the polar projection body in an anisotropic way using two bodies L and K, and we prove that the same happens with the volume of this polar projection body when you see it as a set in matrix space. Okay, so there are other applications, but maybe I will stop here. The other applications are still. So maybe I just stop here. Thank you very much for your attention.